Alright, this is part 2 of video number 3, vapor pressure. If you recall, in part 1, we discussed vapor pressure, what it is. We discussed the differences between a pure solvent and a solvent with a solute. We discussed the two types of solutes, the non-volatile, aka solids, and now we're going to do the volatile solute. So a non-volatile solute, solids, molecular solids and ionic solids, merely dilutes a solvent and inhibits solvent particles from escaping, because again, in a solution of a non-volatile solute and solvent, the solute does not evaporate, just the solvent. So when a non-volatile solute is placed in a solvent, only the solvent escapes. But what happens if you have a solute that also evaporates? What happens if you have a volatile solute? That's what this portion of the video is going to discuss. Alright, ideal versus non-ideal. Now, the ideal solution was a direct relationship between the mole fraction of the solvent and the pressure of the solution. A non-ideal solution is not a direct relationship between the two. A non-ideal solution occurs when there are strong interactions between the solute particles and the solvent particles, two types. Either you have an attractive force or a repulsive force. Alright, a negative deviation from Raoult's law will occur when there is attractive forces going on between the solute and the solvent. The solute that's attracted to the solvent is holding the solvent particles in the liquid form and is just hanging onto them so tight that they cannot escape into the vapor. So your actual pressure of the solution, your experimental one, the one you measure, is going to be less than what you calculate because of that attractive force. Positive deviation from Raoult's law occurs when there's a repulsive force between the solute and the solvent. In that situation, the solute is repulsing the solvent particles, actually kicking them out faster, and the solvent is escaping easier than originally thought. Your actual or your experimental observed pressure of the solution is going to be a larger value than the calculated one, because those are the solvents being kicked out. Raoult's law for a volatile solute, one that the solute and the solvent both evaporate, is very similar to Dalton's with a mixture of gases. So you've got the total pressure above the solution being equal to the pressure of each volatile solute and volatile solvent. You're going to calculate it by the mole fraction of the solute times its pure pressure plus the mole fraction of the solvent times its pure pressure. So it's going to be a sum of the two, and we're going to do an example. Write this down. So just a couple of pieces of information before I continue. I have two volatile liquids. Alright, so a couple of tidbits I wrote down. I have two volatile liquids mixed to form the solution. I have liquid acetone, which is the solute because it's a smaller amount, and liquid chloroform, which is the solvent because it's in a larger quantity. Of the two, I'm going to expect the acetone to be in a larger quantity than the chloroform, only because the acetone has the higher pure vapor pressure. Acetone's is 345 compared to 293. So the acetone evaporates more than the chloroform. right, so here's what I got. I have 5.81 grams of acetone, shortened at ACE. Molar mass given. That's 0.10 moles of acetone in the solution. I have 11.9 grams of chloroform. Molar mass given. 0.1 mole of chloroform in the solution for a grand total of moles of 0.2. Raoult's law for a volatile solute and solvent is the total pressure being equal to the parts added up. Notice that the vapor pressure or the gas phase above this solution is more acetone than it is chloroform, which is exactly what I theorized because the acetone has a higher vapor pressure. I calculate it up and I get a calculated vapor pressure of the gas phase above the solution of 320 torr. I go back in the lab and I end up getting a 260. Well, 260, which is the observed, the actual, the experimental, is less than what I calculated. It's less than 320. So what's going on? Why aren't they equal? Well, they're not equal because the solute-solvent particles must be attractive to each other so that less are escaping. Less escaping means a lower actual vapor pressure. So there's an attractive force going on. That's a negative deviation from Raoult's law when your experimental vapor pressure is less than the one you calculated, the one that's theoretical. And just to put a capper on it, the structures for acetone and chloroform. These are the structures, acetone on the left, chloroform on the right, and there's going to be a strong attraction between the negative end of the acetone and the positive end of the chloroform. That's the end of part 2 of video number 3, vapor pressure.